Let's elucidate quantum cryptanalysis. In this video, we will investigate the quantum algorithm for discrete logarithms. Previously, we defined the function f2, which takes in a pair of inputs, z, h. This is equivalent to the function f2 with the pair of inputs z plus sh, 0. And this is also equivalent to the function f1 with the single input z plus sh. And this evaluates to a to the power of z times p to the power of h. Let's consider a special case where z is equal to 0 and h is equal to 1. So we want the function f2 with the pair of inputs 0, 1. That is equivalent to the function f2 with the pair of inputs s, 0. Now why is that the case? If we set z equal to 0, it disappears over here. And if we set h equal to 1, we're just multiplying s by 1. So that just leaves s as the first input, and we have 0 as the second input. And this is also equivalent to the function f1 with the single input s. And if we evaluate this, we're going to get a to the power of s, and that is, by definition, p. In the discrete logarithm problem, the goal is to find this secret value s. And we're given the public value p, and we're also given a. So given the information of this public value p and this value a, the goal is to find the secret value s. That is the discrete logarithm problem. And in this video, we're going to see how the quantum algorithm for the discrete logarithm works. It is closely related to the quantum algorithm for order finding. Previously, we introduced an algorithm for order finding, and we used a unitary operator, UA. So this unitary operator, UA, had the effect of multiplication by A. So if we consider the state that is labeled by f1 with the input z, this is a beta qubit state, so it requires beta qubits to represent this state. If we consider this unitary operator acting on this quantum state, it will get mapped to the state that is labeled by f1 with the input z plus 1. So we have added 1 to the input over here. That's because this function f1 maps z to a to the power of z mod n. So implicitly, we are doing modular arithmetic. We're working mod n over here when we evaluate these functions. And if you have a value a to the z, and then you multiply by a, you're going to get a to the z plus 1. So z plus 1 is in the exponent. So that is why we have this relationship over here. So that is this unitary operator that we used in the quantum algorithm for order finding. Similarly, we can define another unitary operator, u sub p. And this has the effect of multiplication by p. So we can consider the same state, f1 of z. That's a beta qubit state. And it's going to get mapped to f1 with the input z plus s. So why is this the case? If we apply this unitary operator u sub p, we are multiplying this label by p. But what is p? P is a to the power of s. So we're multiplying by a s times. So it's just like we're applying this unitary operator s times. And the effect of this unitary operator ua is to add 1 to the input. And if we do that s times, we're going to have the addition of s to the input. So that's why this z turns to z plus s. And we're going to use these two unitary operators. Now, let's consider a very important relationship. So if we take the state that is labeled by f1 of 0, this is actually equivalent to a to the power of 0, which is just 1. So imagine we're labeling this state by 1. That would be equivalent to beta minus 1 zeros followed by a final 1. So that is what this state actually means. So imagine we initialize this state and then we apply the unitary operator UA z times. What will this produce? Well, it's going to map to the following state. We're going to have f1 of z. So that's how we produce this state over here in these equations. So if we initialize in f1 of 0, we can produce this state, f1 of z, if we apply UA z times. Every time we apply UA, we are adding 1 to this input. And if we do that z times, we're going to add z to the input. And the starting input is 0. So that's how we go from 0 to z in the input of this function f1. And we can write this state as a superposition of the eigenstates of the unitary operator UA. So we can write this as r to the minus 1/2 times the sum over the index zeta ranging over the integers mod r. So that is 0 up to r minus 1. In total, that is r different values that this index z can take on. And then we have e to the 2 pi I z zeta divided by r. And finally, we have the eigenstates. So these are the eigenstates specified by the index zeta, and they are beta qubit states. So here we're writing this state, f1 of z, as a superposition of the eigenstates of this unitary operator UA. So this is a very important relationship. And now we're going to use that relationship to help us construct the quantum algorithm for discrete logarithms. So consider 3 registers of qubits. We're going to have 2 control registers. Each of the control registers contains alpha qubits. And we also have 1 target register, which contains beta qubits. We need to construct the following quantum state. So we need to prepare the following state. 2 to the minus alpha on 2 times the sum over the index z ranging over the integers mod 2 to the alpha. And then we're going to use this z as the label for an alpha qubit computational basis state. So what we have is a uniform superposition of all of the alpha qubit computational basis states. And note that this index z is ranging over the integers mod 2 to the alpha. So that's all of the values from 0 up to 1 less than 2 to the alpha. So that's not the same as this index zeta. This index zeta ranges from 0 up to 1 less than r, where r is the order of A mod n. So that's the goal of the order finding algorithm, is to find this value r, which appears in this normalization coefficient. But over here, the goal of the discrete logarithm algorithm is to find this secret value s. That is the discrete logarithm. So we've taken care of the first of these control registers. Now we also have another control register, which also contains alpha qubits. And we're going to prepare it in a similar state. So we have that normalization factor of 2 to the minus alpha on 2. Then we have the sum over the index h ranging over the integers mod 2 to the alpha. And then we have h as the label for the alpha qubit computational basis states. And then finally, we have that target register, and the target register needs to be prepared in the state f2 with the pair of inputs z, h. And we have seen this before. This is actually equivalent to this expression in terms of the function f1. So we can rewrite this state in terms of this function f1. Now, once we prepare this quantum state, we need to apply the inverse quantum Fourier transform to the control registers. I'm going to denote that with f sub 2 to the alpha dagger. This dagger tells us we're dealing with the inverse quantum Fourier transform, and this subscript tells us the dimension of the Hilbert space. So we need an inverse quantum Fourier transform to be applied to both of these alpha qubit control registers. How do we prepare this state in the target register? Well, we can use these unitary operators. So let's see how we can do that. We can take UP and we can apply UP H times. And we can also apply UA Z times to the state labeled by 1. Now the state labeled by 1 is the same as this state, F1 of 0. So F1 of 0 is the same as A to the power of 0, and that is 1. And how would we write that out in full if we consider all of the individual qubits in that beta qubit register? You would have a string of beta minus 1 zeros followed by a single 1. So that's what this state is. So if we initialize that state and then apply UA Z times and UP H times, we're going to get the following state. We're going to have F1 with the input Z plus SH. And this is equivalent to this over here. So F1 with the single input Z plus SH, that is equivalent to F2 with the pair of inputs Z, H. So that is the state that we're preparing here. And note that this Z comes from applying UA Z times. So we're adding 1 to the input Z times. And then this SH comes from applying UP H times. So we're adding S H times. And that's why we have the product SH. So that's how we will construct this state. And note that these exponents, Z and H, they are also the labels for these alpha qubit computational basis states. So in the quantum algorithm for discrete logarithms, we want to prepare this quantum state prior to measurement. Let's manipulate this quantum state and see what we're going to measure. So we're going to do some expanding and then we're going to do some rearranging. So first of all, we are going to have 2 to the minus alpha on 2 times the sum over the index Z ranging over the integers mod 2 to the alpha. And then if we expand this inverse quantum Fourier transform acting on the alpha qubit computational basis states, we will get 2 to the minus alpha on 2 times the sum over the index X ranging over the integers mod 2 to the alpha. Then we'll have e to the minus 2 pi I zx 2 to the minus alpha. And we need to change this label from Z to X. And that is an alpha qubit computational basis state in this sum. And we have to do the same thing for this other control register. So that means we're again going to have 2 to the minus alpha on 2 times the sum over the index H ranging over the integers mod 2 to the alpha. And then we're going to have this expanded form of the inverse quantum Fourier transform acting on the alpha qubit computational basis state. So that will give us 2 to the minus alpha on 2 times the sum over the index Y ranging over the integers mod 2 to the alpha e to the minus 2 pi I. And then we're going to have hy 2 to the minus alpha. And we need to change this label from H to Y. So now we've taken care of these control registers and we've introduced these indices X and Y. And you can see that they come in pairs. So we have ZX and over here we have HY in these complex exponentials. And because we're dealing with the inverse quantum Fourier transforms, we have to put a minus sign up here. And now let's consider what's happening to this target register. Well, we can expand it out using this formula over here. So we can expand it out and we're going to get r to the minus 1/2 times the sum over the index zeta ranging over the integers mod r. So this is not mod 2 to the alpha, it's mod r. And then we have e to the 2 pi I, but it's not going to be z because the input is not z, instead it is z plus sh. So this value is the same as this value. And now we can just substitute here, and we're going to have z plus sh times zeta divided by r. And then we have the eigenstates specified by the index zeta, and these are beta qubit states. So you can see we used a similar format in the order finding algorithm. So now we've expanded, let's do some rearranging. We can rearrange. So we see that this blue term corresponds to this blue term, and this blue term corresponds to this blue term, and this red term corresponds to this red term. So now we can rearrange, and that's going to give us r to the minus 1/2 times the sum over the index zeta ranging over the integers mod r. And then we're going to consider this sum over x. So we're going to have the sum over x ranging over the integers mod 2 to the alpha. And now we're going to group together some terms which we can consider as a coefficient. So we're going to take these two normalization coefficients and put them together to give us 2 to the minus alpha. And then we're going to consider the sum over z. And we're going to have the sum over z ranging over the integers mod 2 to the alpha. And now we're going to group this complex exponential with part of this complex exponential. And we're going to get the same coefficients that we found in the quantum order finding algorithm. So we're going to have e to the 2 pi I, and then we'll have zeta divided by r minus, we're going to shift this x, we're going to shift it by plus the alpha bit approximation of zeta divided by r, and then we need to multiply by 2 to the minus alpha, close that bracket, close this bracket, and we're going to raise this to the power of z. Now, if I bring this z back in and undo this shift over here, I can recover the minus x z 2 to the minus alpha term over here. So you see you have x, z, and 2 to the minus alpha. So that is this term over here. And from this term, we can see z multiplies zeta divided by r. So if we bring that z back in, we can see that that term can be recovered. And because I did this shift, I also have to do that shift on the label of this quantum state. So x is going to become x plus the alpha bit approximation of zeta divided by r. And this is an alpha qubit state. So note that when you see this sum over here, when you add x to this alpha bit approximation, we are doing addition mod 2 to the alpha. So here we have addition mod 2 to the alpha in the label of this quantum state. And this is the same format that we saw in the quantum algorithm for order finding. But we're not done yet. We're going to have another line that we have over here because there's many other terms present here. So we're going to consider the sum over the index y. So now we have the sum over the index y, which ranges over the integers mod 2 to the alpha. And then we are going to consider another coefficient. So we're again going to group these normalization coefficients, and that's going to give us 2 to the minus alpha. And then we're going to have a sum over the index h, ranging over the integers mod 2 to the alpha. And we're going to have a similar format over here, but there will be one difference, which is the presence of s. So you can see that s is present over here. When we have h, we also have this factor of s. So that means we're going to have s zeta divided by r, and then we're going to subtract y, but we're going to shift y by the alpha bit approximation of s zeta divided by r. And we need to multiply this by 2 to the minus alpha, close that bracket, and then raise this to the power of h. And if we bring that h back in and we undo this shift, we can recover this minus hy times 2 to the alpha term. And we can also recover this term over here where we have sh times zeta divided by r. So that happens if we bring that h back in. And you can see that this is the same format, but we just have an extra factor of s. And because we did this shift, we also have to shift the label. So we're going to have y plus the alpha bit approximation of s zeta divided by r. And then we also need the eigenstate over here. So that's lambda specified by zeta, and that's a beta qubit state. So this is what we have, and we can identify these as terms in a geometric series. So we're taking a sum over these terms that are in a geometric series. And these are going to give us coefficients. So these sums in red, they're going to give us coefficients that are associated with these terms over here. And we're going to make an approximation. So let's assume that we have chosen alpha such that we get a peak corresponding to x and y both equal to 0. If that is true, if we have chosen a sufficient alpha that allows us to make that approximation, then we're going to have the following quantum state. So this is approximately equal to r to the minus 1/2 times the sum over the index zeta, ranging over the integers mod r. And then this x is going to disappear, and this y is going to disappear. So we're going to have the alpha bit approximation of zeta divided by r. And then we're going to have the alpha bit approximation of s zeta divided by r. And finally, we'll have this eigenstate that is specified by zeta. So this is approximately the quantum state that we're preparing before measurement. Now, if we have a good choice of alpha, and we get a peak in the amplitudes corresponding to x equals 0 and y equals 0, we can make this approximation. So that means we have a very high probability of measuring these alpha bit approximations if we measure the control registers. So what we're interested in is measuring these alpha qubits here and these alpha qubits here. And they are going to give us alpha bit approximations of zeta divided by r and s zeta divided by r. And given those two values, we can extract the value of s. And that allows us to find this secret value s. So let's just have a look at the relationship that these eigenstates satisfy. So if you take the unitary operator UA and you act on one of these eigenstates that are specified by zeta, you're going to get the eigenvalue e to the 2 pi I zeta divided by r. And that multiplies the eigenstate. So you can see that these are eigenstates of the unitary operator UA. And that's what we're going to get over here in this target register, but we don't actually care too much about the result of this measurement. We're only interested in these control registers. So if we measure the qubits in these control registers, we're going to get those alpha bit approximations of these quantities. And if we have those two quantities, we can extract the value of s. So this was the quantum algorithm for discrete logarithms. We just need to prepare this quantum state prior to measurement. And if we have a good choice of alpha, then we will have a really high probability of measuring these states. In the next video, we're going to apply a similar procedure, and that's going to allow us to construct the quantum algorithm for counting targets.